All right, welcome. Today we're going to break down one of the most fundamental structures in our world, and that is the metallic bond.
It really all comes down to this unique and kind of powerful way that metal atoms connect with each other. And to really get it, we've got to start with the atoms themselves.
Before we can even talk about the bond, we have to understand the atoms. Like, what makes a metal a metal?
Okay, so if you picture the periodic table, right? Metals are hanging out over on the left side. And a really key trend here is that atoms get bigger as you go down and to the left. This means metal atoms are usually the giants of their row. They've got these large atomic radii, which is just a fancy way of saying, well, they're big. And because they're so big, their outermost electrons, the valence electrons, are super far away from the pole of that positive nucleus. Think of it like a planet that's way, way out in a solar system. The sun's gravitational pull is pretty weak. It's the same idea here. This means they just don't hold on to those outer electrons very tightly. Actually, they're pretty eager to let them go to get more stable. And you know what? This willingness to just give up electrons, that's the whole key. It leads to a chemical structure that's really unlike anything else. So let's build this thing one step at a time. So picture a whole crowd of these metal atoms, all packed in super close together in a nice, neat lattice. As they get close, they all do the exact same thing. They just let go of their outer electrons. Now think about it for a sec. What happens when a neutral atom loses a negative electron? It becomes a positively charged ion, right? We call these positive ions cations. And what about all those electrons they released? They don't just vanish, nope. They now belong to the entire structure, and they form this kind of mobile sea that just flows all around those new positive ions.
And this is what creates this totally unique setup. You've got this rigid, orderly grid of positive ions just sitting in this fluid, moving sea of shared negative electrons. And these electrons have a cool name. They're called delocalized, which is a great word, by the way. It literally just means they don't belong to any one atom anymore. They belong to the whole shebang, the entire metal crystal.
And that attraction, that's the metallic bond. It's that fundamental force. Positive attracts negative, the electrostatic attraction, but it's happening on a massive scale. So this isn't a bond between just two atoms. No, it's a collective thing. A bond between all the positive ions and that shared sea of electrons that's flowing all around them.
A really great way to think about it is to picture that electron sea as a powerful but flexible glue. The positive ions are like little marbles or something, and the sea of electrons is the glue that's all around them, binding everything together really tightly, but also allowing for a bit of give. Okay, but here's the thing. Not all metallic bonds are created equal. Some are incredibly strong, while others are, well, surprisingly weak. So let's figure out why. It really boils down to two key factors. First up, the more electrons each atom donates to the sea, the more negatively charged that glue becomes, right? And that means a stronger attraction. Simple. Second, if the positive ions themselves are smaller, their positive charge gets way more concentrated. This creates something called a higher charge density, which gives it an even more powerful pull on that electron sea. And you can see this principle in action perfectly when you look at the melting points of different metals. Just look at sodium over on the left. It gives up just one electron, and its melting point is pretty low, right? Under 100 degrees Celsius. Now check out magnesium. It releases 2 electrons, and whoa, look at that jump. Its melting point is over 600 degrees. Then you get to aluminum, which gives up 3, making its bond even stronger. It's so clear. More electrons in the sea means a stronger glue, and that means you need a lot more energy to break it all apart. So, this whole sea of electrons model is pretty neat, but is it actually useful? Oh, absolutely. Let's see how this one idea perfectly explains the classic properties of metals that we see all around us every single day. Remember that question from the beginning about the wire? Well, here's your answer. It's the mobile electron sea. These electrons are basically free-moving little bits of charge, so when you apply a voltage across the metal wire, you're creating an electric field that just pushes these free electrons along. That creates a flow of charge, and guess what? That is exactly what an electric current is. It's as simple as that. And this idea also explains why some metals are so soft and others are incredibly hard. Let's take sodium again. It only releases 1 electron per atom, so that creates a pretty weak bond, right? So weak you can literally cut it with a butter knife. But then you have iron. Iron releases multiple electrons, creating a much denser, much more negatively charged electron sea. That stronger glue gives you a way, way stronger bond.
making it hard enough to build skyscrapers with. See? It all just comes back to the strength of that bond. All right, so let's wrap this up. Let's recap what we've learned about this amazing structure that quite literally shapes the world all around us. If there's one big idea to take away from all this, it's this simple but really powerful model. You've got an orderly grid of positive ions, and they're all held together by a shared mobile sea of electrons. From just that one concept, we can understand so many of the properties that make metals just so incredibly useful to us. It's just a fantastic reminder, isn't it, that right beneath the surface of the ordinary things we see every day, there are these incredibly elegant and powerful structures that make it all possible. Thanks so much for joining me.